Hey chemists, it's Dr. O'Malley here, and we're going to start our solid state chemistry unit. Solids can be described as either a crystal or a glass. Everything that can exist in the solid state either has a highly ordered atomic structure at the atomic scale, or it's amorphous. It has a very disordered state. So things like diamonds or snowflakes or even salt crystals and sugar crystals, things we find in our kitchen, can exist in a highly ordered crystalline state. And they could exist in an amorphous state. Things like wax and plastics are usually more amorphous, and that's actually known as a glass, even though we think of the word glass colloquially as the silica that forms window panes and things like that. Anything that's an amorphous solid can be considered a glass. And anything that's highly ordered can be a crystal. Here's an example of a very rare but beautiful naturally occurring set of crystals. These are the basalt columns in Hofsís, Iceland. And that's actually me a few years ago when I got to visit them on the coast. They're made of this volcanic rock that are magnesium iron silicate crystals, and they exist in these large, what look like hexagonal columns coming out of the ground right on the coast. They're quite beautiful. And on a macroscopic scale, we can see some order to the way they're arranged. And what that is it's indicative of how they're arranged on a microscopic scale at the atomic level. Here's a chart that shows various types of crystal structures that exist. You actually did a lab related to this in your 10th grade class when you made small crystals of copper sulfate and looked at their properties just visually through a magnifying glass or something like that. And what that shows you is the arrangement on a large scale. Even though they were small crystals, you could see them with the eye. That shows you how they're arranged at the atomic scale. Today we're going to look at the three most common crystal lattices, or three that are most commonly studied, namely the cubic lattices, the simple cubic, the body-centered cubic, also called the volume-centered, and the face-centered cubic cells. But it's important to keep in mind that this is just a zoomed-in picture of what's happening on a much larger scale. These exist in a lattice, atoms packed together in the solid state when they're a crystal in a continuum of atoms. Imagine them like spheres packed together in giant spaces, and they can arrange themselves differently. And on the screen right now are the three different lattices that are simple cubic, body-centered cubic, and face-centered cubic. And the reason we call them that is because if you highlight one specific repeating three-dimensional cube, we call that a unit cell, you see what looks like this. The simple cubic arrangement, the repeating cell, is just a sphere at each corner, an atom at each corner of that cube. Whereas the repeating unit in a body-centered cubic unit cell has that same corner repeating pattern, but it's also a bit denser. There is another atom, another sphere in the very middle of each repeating cube. And then the face-centered cubic is different yet again, this time with a repeating cell that looks like that all the way to the right, which has an atom at every face of the six-sided cube. That's a picture that shows these cubic cells with the entire sphere, but what I'm going to do is chop away what's not inside the cube, and you get a picture that looks like that. And that's a little more indicative of the space-filling properties that we see, the simple cubic, the body-centered cubic, and the face-centered cubic. So if you look at your notes, this is where we begin with those three types of unit cells. And the first thing I want to draw attention to is simply how many atoms are in these repeating unit cells that we're looking at. If you look at the first one, the simple cubic, there's an atom at each corner, and that's it. So we have a total of 8 corners, but inside the cell, there's not actually an entire atom. Each of those corners is just 1/8 of an atom. If you picture 8 of those, you would get an entire sphere, but each corner is only 1/8 of an atom, so there's an eighth at each corner. So we get 8/8, and you have 1 atom in the entire cell when you just add them together. The body-centered cubic still has those 8 corners, but it also has this one entire atom in the very center, one whole one. So how many atoms are in one repeating cell? Well, there's 1 plus 8/8, and I get 2. So there's 2 atoms of whatever atom we're talking about. They're just different colors in this picture to let you see them differently. You could have this type of arrangement with a crystal of a pure element where all the atoms are the same. That's also possible. What about the third one? Well, the third one still has those eighths at each corner, so there's 8/8. But then we have these faces. They're just shaded in blue to make them look different. And if I think about how many faces there are in a cube, well, there's 6 faces, and each of them have what look like a half of an atom. So the total would be 6 halves and 8 eighths. So I get 4 atoms in the face-centered cubic. So they have different packing densities in each repeating unit cell. And we can use that with some other properties of the atoms to look at macroscopic properties. And that's what we're going to do today. So I'm actually going to pan over to the handwritten portion of this, and we are going to use properties of the atoms at an atomic scale to look at their macroscopic properties. So the first problem says, if iron happens to crystallize in a body-centered cubic unit cell, and we know its atomic mass, its atomic radius, can we get the density of the iron? And yes, we can. So let's walk through that. First of all, we're looking at the atomic scale. So if I want the mass of the atoms, well, we just said that in a body-centered cubic unit cell, there's 2 atoms in the cell. And remember Avogadro's number. There's a mole of atoms per 6 times 10 to the 23 atoms. So now we're in moles of a substance, and now we can turn that into mass. We're talking iron, and they were very nice. They gave us the atomic mass of iron, 55.85. So I just multiply what I have times 55.85 grams per mole, and you can see dimensional analysis working as always. Atoms cancel with atoms, moles cancel with moles, and we get a very small number, no surprise, 1.86 times 10 to the negative 22 grams. Very small number. So that's just the mass of 2 atoms of iron, because that's within the cell. If in order to get the density, I need the volume. So I want the volume, but I want the volume of just that cube. So there's a picture of the cube off to the right, and it's often written D for the edge length. This is just the edge length of the cell. Sometimes you'll see A, also called the lattice constant. It just means the linear dimension that encompasses the cube. But if I think about the type of cell this is a body-centered cubic cell, and we just talked about how many atoms are in there. Where do I have atom-to-atom contact? I don't actually have atoms touching each other along the edge. There is a space. And there's not even atoms touching each other along the diagonal of a face. The only place I have atoms touching each other from one edge of the sphere of an atom to the other is actually along the diagonal of the entire cube. That would be one iron atom, or actually one radius of an iron atom in that corner, another iron atom going through the very center, and then one more fraction of an atom on the other side. And they were very kind and gave us a picture that sort of already shows us this embedded in this picture. So this is the radius. R is equal to the radius. And what we have is an eighth of an atom giving me 1 radius, and then an entire atom, 2 radii, and then another corner of an atom, another radius. So that's how we get R, 2R, and another R. So we get 4R along that diagonal. And then if I look for a right triangle, I spy one. It's sort of already highlighted for us. There, and there along the diagonal of the cube. I have the edge length. I have 4R along that hypotenuse. And then I also have the hypotenuse of one of the faces of the cube. And if you use a simple Pythagorean theorem, knowing that this is D, and also this is D, every edge length is D. Oh, so this is D root 2. And now I can use the Pythagorean theorem yet again and derive an expression for the edge length in terms of the radius, because that's what I have. I know that the volume of the cube is going to be the edge cubed, and I need to turn that edge length into something in terms of the radius. So, and I'm going to use this right triangle that we just wrote out here. So a squared, which is d squared, plus b squared, d root 2 squared, is equal to c squared, 4r squared. That's the Pythagorean theorem. A squared plus b squared equals c squared. And this simplifies down to 3d squared is equal to 16r squared, which means that the edge length d is 4r over root 3. So the reason we did that is so that we have an expression for the edge length of the cube in terms of the radius, and we can actually solve for the volume of the cube. So the volume of the cube is simply the edge length cubed, d cubed, which is 4r over root 3 cubed. And we know what r is. R is the radius of the iron atoms. 126 picometers is what's given to us. So that means I have 4 times 126 picometers divided by root 3 cubit. That's going to give me a volume in cubic picometers. I want cubic centimeters. So I need to do a conversion just from one prefix to another. To get it into centimeters and out of picometers, well, there's 100 centimeters inside 10 to the 12 picometers. That's the linear conversion. But if I put a pair of parentheses around it in cubit, now you get the cubic conversion. And then I just have to do that math. You get a very small volume, no surprise. I plug it in, I get 2.46 times 10 to the negative 23 cubic centimeters. So that was our mass of iron atoms in the cube, and then we have our volume of iron atoms in the same cube. Now let's just get the density. What's the density? The density, I'm going to write out density so I'm not confused with d, which is the edge length, is the mass over the volume. And we have the numbers we just solved for up above. 1.86 times 10 to the negative 22 grams divided by 2.46 times 10 to the negative 23 cubic centimeters. And I can tell I'm going to get a reasonable number. These very small numbers divided by each other, I get something in the regular tens base or ones base. I get 7.56 grams per cubic centimeter once you substitute and solve. And you can look up in a table what the reported density of iron atoms is, even though it exists in different crystal structures. You can get a rough approximation just finding, what's the density of iron. One table I have from your textbook tells me that it's 7.86 grams per cubic centimeter. So what we observe experimentally on a macroscopic scale is matched by what we calculate on the atomic scale. And that's just one thing that we can do with crystal structures. What we see on a very, very small scale, we can zoom out and we get something that's observable and measurable on a macroscopic scale because of that repeating pattern on a very small scale. So I want to wrap up and just try another one. Let's do one that involves a different unit cell. Let's look at the face-centered unit cell, and we're going to be asked to do the same thing. This is a different unit cell. It's FCC. These are silver atoms, which are slightly larger, 144 picometers, and I want to get the density. So first up, just to sort of repeat what we did before, the mass of atoms inside the cell. Well, there's 4 atoms in an FCC cell. If you look all the way at the top, we calculated that. Times there's a mole per Avogadro's number of atoms. And then multiply by the atomic mass of silver. That's 107.87 if you look it up on a periodic table. Grams per mole, we get a very small number, 7.17 times 10 to the negative 22 grams. Now the volume is going to be the edge length cubed. So once again, we need an expression of the edge length of this unit cell in terms of the radius of a silver atom. The picture that's given to us is very helpful, so we don't have to do as much thinking. Here's an edge length d. And unlike the body-centered cubic unit cell, this one actually has atoms touching other atoms along a face. So my edge length in terms of radius is not what we calculated for BCC. It's different. I have a right triangle right on the face of any of the faces of this cube. So I could look at one edge, another edge, and then the hypotenuse, the diagonal of one of the faces. And I can write an expression d squared plus d squared is equal to 2r quantity squared. You simplify that, you get that the edge length d is just 2 radius root 2. So we can use that when we're getting our volume. So the volume is d cubed, so that's 2r root 2 cubed. So that's the quantity 2 times 144 picometers times root 2 cubed. Once again, that's going to be cubic picometers. So I'm going to use the same conversion I had before, 100 centimeters per 10 to the 12 picometers, and then cubit whole thing. And that gives me a volume of 6.76 times 10 to the negative 23 cubic centimeters. And then my density is the mass over the volume. I'm just going to plug those numbers in. I'm not going to write them out again. I get 10.6 grams per cubic centimeter. And if you look it up, the same table I was looking at before that showed me iron's value, the reported density of silver is 10.5. So once again, we get a really nice result. Taking macroscopic properties, we can compare them with what we get from atomic scale properties. So that's how we use things related to crystal structures so far, just to get the density of materials by looking at the density of a handful of atoms in the way they pack together in a crystal lattice. Those are the three common types of unit cells that are cubic. There are others, but we're going to focus on those. And most of this lesson was really just about geometry and dimensional analysis. We'll look forward to some other unit cells and see some other applications of crystals in chemistry.